Okay. Took me a while to get set up. I wanted to do a quick overview of this new project, the progress that I've done so far. So, I basically want the computer to play Brawl Stars with me. Brawl Stars is played on an Android phone, and so the basic idea in general, I know that what I wanted to do is somehow the computer gets a hold of the game being played, so it can grab frames, it can analyze what's going on in the game, and control the player, like a true AI. Now, there's a few ways of doing this, and a few ways that I thought about. So basically, what I settled on right now is my PC is here, and the phone is here. The phone. Arduino physically moves physical thumbs on the phone and interacts with the screen. And the video feed goes right into the PC, into OBS, which tacks on an NDI source and is received by Unity. And while Unity uses OpenCV to analyze the pictures. I haven't thought about that. I've thought a little bit about that process, but let's not get ahead of ourselves. And also controls the Arduino via serial. Now, originally I wanted a camera to look at the screen and have that go right into Unity, but there's going to be issues of scaling and resolution and glare on the screen. If I can get this direct video feed, I can break the frame into pixels that are always going to be consistent, no matter the color of which are going to be consistent, no matter where the physical light is coming from, right? Is this loud enough? I don't even know. Anyways, so that's the general idea that I'm working on right now. But the other ways that this could be done, well, let's say on the same PC, we can run BlueStacks, right? And BlueStacks is a container, a VM type of deal that runs Android. It runs an Android operating system, and you can basically have the same things on your phone now on your PC. The cool thing about BlueStacks is that it does have a keyboard bindings, so you can. But there's some issues with it. So there's keyboard bindings, and so originally I thought, okay, so basically you can map a key to a swipe. The problem is not that. The problem is that it only allows for what's the issue? Hold on. Yeah, the types of swipes. So it only allowed for, let's say, keys 1, 2, 3, 4, 5, 6, 7, 8, 9, and you could pressing 2 would generate a forward, would emulate a forward slash, right? And a diagonal slash. But that's the resolution that you have here is only 45 degrees. For rotation Brawlstars requires more accurate directional controls. But sometimes you'll need to, yeah. But that would have been if I were able to, for example, instead of getting key bindings, I could set the angle. Oh shoot. Yeah, that's not possible. But that solution, if this were any other game, this would have been a great solution because BlueStacks has key bindings, and BlueStacks runs the game. The same PC, I can grab the screen, a screen capture of the game into Unity. Unity does its OpenCV thing, and now it can, with C# and .NET, whatever 2.5 even had keyboard emulation, keystroke emulation. I forget there's like a Windows library that can do that. I forget what it is, but anyways, you could do keyboard bindings back to BlueStacks, and everything runs on the same PC, and that would be probably the fastest, depending on what the game is, because you still have to run the graphics for the game, and also Unity would need to. Screen capture is not that expensive. It's going to be the OpenCV tracking. Now this is going to be the bottleneck. This is going to be actually the one thing that I'll need to optimize the most, because in any case. So that would be the one solution. The other, to alleviate processing, I could do 2 PCs. Yeah, PC1 and PC2. Now, this solution was kind of funky. So on PC2 I have BlueStacks playing, and what was I? The video can go either through the network using NDI, which is then going to be received by Unity with the NDI plugin, and use OpenCV. This does not change OpenCV. And now the keyboard, the control for the other PC, instead of, I could do a UDP through the network and have a UDP receiver here that'll just do that keyboard emulation, or I could have an Arduino Leonardo, because that can emulate an HID controller, so I can set it to be a keyboard, and then use a, since the COM port is going to be used, I can use SPI to another Arduino and use serial. So that would be kind of funky. The other way would be to just hack an actual physical keyboard and just bring out wires from the keys that I set up as key bindings in BlueStacks. That is controlled by an Arduino, and then serial this way. And to make it even faster, forget the network, I could even have, let me see, yeah, I can set up a secondary display into a video card that goes right into here, and that will be grabbed as a camera source, and that goes also directly to Unity OpenCV. That would be the fastest. That would be using 2 computers, a hacked keyboard. One computer would be playing the game on BlueStacks, the other would be looking at the frames, figuring out how to control the player, and doing that by controlling the Arduino, which is then going to be clicking literal keys that are going to be received by the first computer. But that's just too much of a process. This could be, since this is a 3v3 game, could use this as a to pursue this just in case, just for fun. I think that would be pretty interesting. In any case, the solution right now is, so I've tried a couple of things to control what's on its screen. Let me show you. So a couple of months ago, where was it? This thing? No. Yeah, it was a GIF. Where did I put that? 1 second. Yeah, so I figured out a way to interact with a touch screen using an Arduino. And this is an iPad, and as you can see here, this I have an actual solenoid, and yeah, the little touch pad thing, the little touch. It's a felt tip. It's one of the. It comes from the tips of those tablet pens, and it's going up and down, clicking. No, it is not. Sorry. Sorry. This is just a relay closing the circuit. So basically, this is what I learned. Let me go back to this on top. So these screens are capacitive screens. So the way they work is they measure voltage drops. So there's receptors for vertical columns of conductive material that if you do not touch, the current will be, the voltage will stay even across from source to destination, and same thing across. Now what happens is when you touch the screen in a certain position, you end up lowering the voltage because you're grounding the screen basically, and there's a drop of voltage in this location, which is then registered and by the indices of these receptors, these sensors, and this would be index 0, 1, 2, and whatever grid 2 to 2, 0, 1, 2, 3, and that would be sent to the operating system, which is the center of the operating system, checks it and registers a touch there. Now to emulate this, I, without my fingers, found the best way to do it is to use the audio jack going into the phone, because that is the outer shield touches ground, and use that to drop voltage on different positions. Now I've tried, so the plate that touches the screen needs to be big enough for the screen to register a voltage drop. I've tried a couple ideas. I tried solution. It's not a so the let me show you the final. It's these little tips of tablet pens. They're very good conductors, and they're also manufactured to be all the same size, which is very helpful for my purpose. I tried these medical, not probes, but what do they call them? Yeah, that's the little probes they put on you when they have to measure your like heart rate or whatnot. So I ordered a couple from Amazon, but yeah, here they are. Pretty big. Really, that gooey gel is very sticky. It works really well, except that it's really big and it does not. It's very hard to move and leaves goo everywhere. That is the most optimal thing. It doesn't even have wires going like copper wires going in. It's like a mesh of fiber, so it's very conductive and it really it really works the best. So I even tried to modify the one of these pads, and I cut four of them into four little squares, and yeah, once that is pushed onto the screen, as soon as you, still sticky as heck, as soon as you figure out a good way to apply pressure evenly all around. Now this is just a piece of post-it note and hot glue, and the other side is left bare. I try to put a row and like an X, a vertical line, a horizontal line. The pink line is hot glue, and that is definitely not conductive because I figured I didn't want to have, you know, one button affect another. Now, it kind of worked a little bit. Let me show you the video result. Be here, and let's view this bad boy. Oh no, this is not it. Sorry. Let me go back. Actually, don't have a video of that because that was kind of crappy. But that's a good segue to the more complex. So that I use that for pad array. This one, back to, so I used this, and it was convincing enough to try to make an array of these sensor pads that would be able to grab a more of a resolution when it comes to radial directions. So with a 4 pad, so you can kind of emulate that on the game itself. If you were to put 2 fingers, instead of swiping, you could put a first finger on one location and then another finger right next to the first location, and then releasing the first finger, and you can, sure enough, emulate a swipe. It doesn't work that well all the time. It's consistency doing with your fingers is pretty hard. So I figured I could do it with a an Arduino. So these pads are positioned this way, and each one of them is connected to a relay that is controlled by Arduino, and once the relay is closed, it goes to ground, which is the little jack thing. And I was able to, with Arduino, turn on one pad and then the next pad, and then release the first pad, and I was able to get some sort of motion. Now, like I said, this had to be placed really flush onto the screen, and doing that reliably was not an option. So after that, I decided to 3D print a part and have, so basically what I did was a circular, like a disc with these little nubs that would come out from a top view would be this one nub in the center, top, down, left, right, and then fit the diagonals in there, and then fit those nubs. So these would be cylinders, sticking up with a hole in the center to allow a wire to go in, and then these cylinders would be capped by the tablet pen tips on top. And I can show you what that looked like, and that's what the video. That's the video of what I was saying. I have a video of. So here it is, and I have 9 of them, and they're all going to 9 relays, and controlled by an Arduino Mega. That I can tell you the result. That's the thing that I had filmed. It's on the YouTubes. Here, change. So yeah, this is the pad, and I can get the character to move, once again, not very reliably, because once again, I have to, placing this pad has to be very precise, and needs to be consistent, and I need to remove this phone, and I'm not going to keep it. I mean, I could, but that's not very very efficient. Oh, I'd have to update my tools. Anyways, so that kind of worked, but I figured the best way to do it is to just emulate an actual movement. And let me show you it in the works. And that's actually way more reliable than any other solution. As we can see, the character moves. It's very consistent. So after that, I tried to skip a couple steps and just I'll show you. So this idea came from, I was watching something about a crab holding a pen. It's a combination of a couple of things. Lego part, but in order to move across 2 dimensions, the way plotters do it, well, they have rails, and then I could have one horizontal rail, another one, and have a sort of motor that will carry a vertical beam across left and right over the screen, and on this beam will be a roller or another head that will be able to go up and down. This way I can reach any position on the screen. The only thing is Brawlstar requires two fingers. So this would be good for emulating touches, like if you want to browse, like have an AI just control your phone with like single fingers. That could emulate a tap, a swipe, and pretty much reach anywhere around the screen. I could have 2 of these little systems to, maneuver across 2 halves of the screen, but it's going to need very small motors, and it's probably not going to fit. I'm not going to have that much displacement. Another way to do that, I guess, would be to have one servo, one arm here, and then on the arm another servo and another arm, and effectively by controlling these 2 angles, you could reach a huge, a good area of the screen. As you can see, any point here all the way down can be reachable, as long as that covers even half of my screen. That would be good. The problem with this is precision. Yes, because now we have one arm that's going to be moving with the weight of another servo on it. I could stack the servos at the base and have actuators and, you know, push-pull actuators that will just move that, but then once again, accuracy is going to be lacking. I could, I mean, it's not that big of a distance. Yeah, I guess could be an option. And yeah, definitely finding the inverse kinematic on this would be a lot simpler. Because all I'd have to do, so if I want that point, and I know the arm's length A, B, then all I would need to do is, yeah, so any point could be represented as this angle, theta A, and I guess this angle, theta B, which is the angle of the servo. And the way to find that, so I have this coordinate and I know it's x and it's y. So I have this distance. I can find this angle. So I can find the length c, this hypotenuse, either by using the y and the x and y coordinates, and using just going c squared is equal to c is the square root of x squared plus y squared, or I could use the cosine rule using this triangle here. So once I have this little angle here, so I don't have that yet, I just have the hypotenuse here. So once I have that, knowing this is a right angle, I can definitely find, and I have, yeah, SOHCAHTOA, I can find this little guy, and I can find this angle. And also using the cosine rule or the sine rule, I can find, knowing A, B, and C for a side triangle, I can find this angle and that angle. Once I have this, theta alpha is this plus that, and this one would be to do anything parallel to that? No. Well, it's 180 minus theta c. So that would be simpler to find. I kind of did something like that for the leg of my robot, and that was just the side view. The robot dog also was able to move on third axis. Yeah. So that's good, but you know what? Yeah, I know why I did not choose this solution. Because of imprecision caused by momentum. If I want it to play a Brawlstars and it be fast and responsive, I think that moving these two arm linkage will just cause momentum, and therefore it's not, the problem is not doing the directional swipes, it's the coming back to the center. So if you have the joystick and it starts swiping up quickly, that's fine, because even if it jitters a little bit here, the game will register that as a swipe, a diagonal swipe. But when I want to release, therefore stop my character from moving, what I would do with my fingers is I would just release the screen. Releasing the screen here would require a third motor or solenoid. Yeah, you know what? This idea could work. Now that I'm thinking about it again, yeah, it'll just be one servo at the base here and a second one stacked, and this little arm thing, and just a pokey guy can just have everything away. The touch head will be here. I can even have a solenoid. And if my screen is like this, I can. Let's. You know what? I might implement that as the other thumb. So what I have now is this. Yeah, it's two servos away from the screen, and the way now I can definitely reach less of an, yeah, I can only interact with a smaller area with this, but it's more accurate, less susceptible to jitter. And I have not figured out the inverse kinematic for this, and actually that should be a good time to do so. I'm gonna get something to drink. It's 3 o'clock. I'm gonna take a little break, get something to drink, and we're gonna do. Or I'm gonna do the inverse kinematics for this bad boy, because right now the way it works is I just literally took the model, moved this point around, so in order to hit a middle point on the screen, these radial points, I hard-coded the angles for the servos directly. And so therefore, if I were to say move north, the two servos know exactly what angle to go to reach this point and swipe back to the center. Now, it's cool and all, but the whole point of doing this is to have more resolution, more angular resolution, because I don't just want to move my character up or north or northeast. I want to have as many possible points of contact so I can navigate the map more accurately. And that also needs to be done on the other thumb, because the other thumb controls the attack. So yeah, so basically, instead of using this dumb system, ultimately I'd like Unity to send a directional unit vector. So when Unity has located my player and has located an enemy or obstacle or whatever, this unit vector needs to be sent to the Arduino. The Arduino needs to be able to move 2 servos. In order to make a 4-arm linkage reach a point that would be the vector pointing from the center of the controller. So the GUI controller has a center that's right here, and if Unity decides that needs to move the controller in the direction of this unit vector, it could have to be. I'd like Unity to do. Shoot, you know what? I'd like Unity to do the servo calculation, because in any case, it's going to be faster than the Arduino. Okay, so yeah, this way, if not a unit vector, any sort of vector. That way, my little thumbstick guy can actually go from a position on the screen that is. So I take my phone, cut it in half, cut that in half, and have it can go from the center of the screen to anywhere on this in this radius by having Unity by having a vector sent to the Arduino. That was the first idea, but I think about it, what makes more sense? Unity only speak Unity speak and has no idea that there are two servos that are going to translate that vector into something they understand, or well, Unity will be able to calculate that faster, even after having done the whole OpenCV screen capture and analysis and tracking. But if I were to change the servos, then I would have to change the code in Unity. How often do I change the servos? Oh man. The other way that makes more sense is Unity sending the vector. Shit, a vector is going to be a float. Okay, two floats. It's a vector 2. I'm thinking about the size of the messages. Either send 2 integers that are never going to be bigger than 360. Well, in our case, 180. So 2 bytes versus, well, I could also send a trimmed, the resolution on the servo is not that big anyways, so I don't need to send precise floats. I can just I'd have to test it. I'd have to test what's faster. Right now I'll just keep it as Arduino receives a vector and figures out how to move the 2 servos. And that's what we'll do in 2 seconds. Just get some to drink. All right. We'll have time to code it up, I guess. All right, I need either a piece of paper or let's think about this. Let's measure what we have. 39, and then these Lego pieces 32 and 48, I think. Yeah. And 48. So on those, I have 2 servos. And the axis to axis is 39. Oh, I need my there we go. Hello, hello, 1, 2. That works. Each arm is 32, 48, and then potentially and I want to get Embroil to input just XY and output this angle. We're going to go theta servo right and theta servo left. And yeah, it goes from 0 to 180 in counterclockwise. So that's the problem to solve. So let's see. So how about we need a position, but we don't even know where to anchor ourselves from. I have an idea. So this would be okay to maximize our range. When we input 0, 0, 0, we kind of want to be, if this is my phone, we really want to be, this is half the phone and half. We'd like to be right here. That way, if we can make a square here, we can have control over this entire half, or depending on how, okay, so we need to find, to start everything from this center. So how about, I'm gonna try to, oh yeah, so first I'm gonna try to get when it's, the extension is maximal, what's the toppest most that it can get, because I still don't know if it could actually reach from top to bottom. So let's see what kind of numbers we get when this is completely stretched. So it would be it's like that, and we have 32 and 40. Let's have 80, and we're just going to need to find how far up from the center that would be. So this is 39 divided by 2. Calculators. We're going to need a calculator anyways, because I'm going to be doing all sorts of sine, cosine stuff. So I think I'm just going to use my phone, because now my TI-83 has a problem with, there's a whole column that does not, let's see this, it's supposed to be a 0. There's a whole column of pixel and it's kind of dead. And it's annoying. There's another one too on the other side. So it's frustrating. And sometimes it's very misleading. There's one that goes away that's like the, whichever column is exactly where the decimal point should be. And yeah, So we're going to call this, I'm going to start giving our this would be arm 1 right, this would be arm 1 left, arm 2 right, and arm 2 left. This between these servos are going to call D, and therefore this is going to be half of D. Max Y displacement is going to be let's see, AR A2. We're going to do with this side A2R plus A1R square. So it's like let's see. No, this square. Let's see. This is my hypotenuse. So the hypotenuse is h squared is equal to half of d squared plus our y squared, right? We get h squared minus d over 2 squared equal to y square root of that. Okay, so let's start putting this. Max y is going to be square root of A2R squared plus d over 2 squared. We got that point. Now the lowest point, if you think about it, the lowest point is going to be, it won't be able to go any further than when this arm is all the way stretched out this way, when the arm 2s are horizontal. There's actually we never want to reach this point, because this is very dangerous. Neither do we ever want to reach the full stretch. So what I should have done is figure out the max angles. Well, I cannot say that. I cannot say that this is the lowest, you know, the furthest. All I'm saying is we do not ever want to get into this situation, because with momentum, if we had stretched these arms out too fast, this point would have gone further down than the horizontal, and therefore when the servos would close back up, trying to bring this point back up, well, as you can see, this point is going to not go the right way. So we never want to reach this critical point, but this critical point only is a critical point for any point on this vertical line, because we will need to go further that way if we ever need to reach a point, let's say far out to the top right. This is going to need to curve to more this way, to that, and that's going to stretch out that way. So we need that. We cannot say that this is the most critical, but we need to find the display of the max. I just want to find what this distance is, the max distance from it's going further, the furthest top to the furthest low. How do we find this? So that would be this line, which is, we said 8. This is 32, and this is d over 2. We know this is 90 degrees, and this is 90 degrees. Oh, if I subtract half d from this 48, then now I'm going to have, this would be 48 minus d over 2, and if I have this length and this length, I can find the remaining length. No, I cannot. I need an angle. This was d over 2 as well. See, jeez. How do I get that? I would need, you can find this. This is possible to find here. I have 48. I have 32. I have this. Yeah, there's only one spot that allows that to happen. Let's see. definitely is a closed box. I mean, no, it's not. It's not. It's not. Yes, it is. There's no way you can move this 48 horizontally any other spot. Yeah, there's no way you can do that with this being 32 and this being known. So what's the problem? Oh, hey, what am I talking about? Yeah, I think I got it. I think I got it. This is a 90-degree angle. This is 48 minus t over 2. I have this distance, I have this distance, and this is a 90-degree angle. I can find this angle. And once I find this angle, I can find... Oh, if it's a 90-degree angle, I don't even need that. Yeah, there we go. That's the height. That's the height. Oh my fucking god. That took forever. Okay, so the way to do this is... yeah, well, I didn't even look at it the other way. Jesus, we have... This is a 90-degree angle. It's a right triangle. Jeez, I'm too tired. So we have the whole hypotenuse square. So what do we call this? So this distance, this is going to be min y. Jeez, this took forever. The rest should flow like water, right? So this min y, we have 32 squared is equal to our min y squared plus blah blah squared. And so we want to take this blah blah square out of there. So it's 32 squared minus this 48 minus t over 2 squared, the square root of. Okay, so it's the square root of a1 r squared minus a2 r minus d over 2, the whole thing squared. Right, did I do that right? H equals a and b. A equals a squared plus b squared, a squared. So what we want to extract is this b, so we subtract this a from both sides, so it's a squared minus a squared equals b squared, and we just do that, and thus we have our b. Yes. Okay, so that's right. So now that we have this, now it would be nice to have the center point. So our center point of the full top-down displacement. This would be our world center. Center is going to be on the x-axis. It's going to be 0. It's going to be a vector, and it's going to be max y minus min y divided by 2. Okay, so now we have this point. This is the point that when both servos are ultimately going to be at this, there's going to be a certain angle, all we know is they're definitely going to be equal. And at this certain angle, the pointer will be exactly in the center. It will be at this position relative to this point. Relative to the center between servo left's axis and servo right's axis. And that's going to be, it's technically, this is our real 0, 0. Servos are, these are physical 0, 0, but this is our pence position 0, 0 at the center, like the one at the position that will maximize a radius of, maximize the radius for all the locations that it can touch on its half of the screen. Okay, so we have that point in world. Now, from that point, and that would be the equivalent of me putting my left thumb in the center of the GUI joystick. And if my brain wants my thumb to move up, it sends a vector going, vector 1, 2, which is up in that diagonal direction upright. And I do it. And that's what I want Unity to do. They'll just send a vector in which will be translated to a position relative to that 0, 0 center between the max of where it can reach and the lowest of where it can reach. Now the next step is figuring out this angle. We called theta servo right. Knowing this, which is arm 1 R, arm 2 R, we know those. And now we know our relative displacements. We know this. This is going to be, we're going to call this, CY. And anything is going to be, so a new point, let's see a new point. Let's see the Unity sends vector 1, 1. Right. We want to be touching here. Now what we want to do is figure out where does the servo have to move? And what does the other servo have to move in order to reach that point? Let's think about this. Okay, well, first thing I can see. It's going to be this. Should know. Let's not even look at the left side yet. This is our x displacement for that vector that was sent, and this is our y displacement from the center, so we know exactly what this is. We know that. yeah, well, we have to figure out this mirror line. We're going to call it M. And so M, once again, the Pythagorean theorem, M squared would be equal to this. So let's go M is going to be equal to the square root of center CY. Oh, center, and this is actually CY. So CY plus the, sorry, let's just, CY plus the y that was given to us. That displacement squared plus x squared. That would give us this distance. We most likely are going to have to find out some angles too. Then I have M. We're going to have to break this up into, see if I can find out what this is. We have M, we have D2. If I find this angle, I can find the length of that. So first, let's find this angle. This is going to be called theta M. And theta M is just going to be 90 minus this angle. And that angle is going to be this angle, we're going to call it theta offset. Theta offset. Theta offset is equal to inverse sine opposite divided by hypotenuse. So of x divided by m that we just got. We have this. Theta m is now 90 minus theta offset. We have this angle. We have this and that. Oh. What was the let's see. Make some space here. Yeti comes out with this. So basically, if you have a triangle with A and B and C for sides, then and this angle theta for side. It was, I think it was a, well, that side was C is the square root of 2 that squeeze the angle, so A squared plus B squared minus 2AB times the cosine of theta. So that we have to remember. And the other way to extract the cosine of theta, we had so it's the two that's squeezed minus the other, so it's a squared plus b squared minus c squared, and all that over 2ab. Now, knowing that, let's need to keep that. Yeah, so because now we're in this situation where we have a is m and our b is half that, so we can figure out what this big what do we call that is going to be our main hr and mr. No, that's m. M is the mirror; it stays in the center. So HR, human resources. So HR is going to be equal to the square root of our a squared is going to be m squared plus d over 2 squared minus 2m a to 2ab, so m d over 2 times times the cosine of theta m, which we just got. Now we have this, and we have this and that. We have to do the same thing. Oh, wait. Yeah. We have to find this angle and this angle. It's going to be theta HR HR2. So we're going to need theta HR1, which is going to be the inverse cosine. Here's this guy of so A and B are these guys, so it's d over 2 squared plus HR squared minus m squared divided by 2 d over 2 squared. Oh, sorry, 2 AB. D over 2 dm over 2 dm over 2. So just dm. And theta HR2 is going to be inverse cosine of A1R squared plus HR. We're going to need to catch some values. Minus A2R squared. And now we finally have the angle theta SR, just for the right one, is equal to 180 minus theta R1 plus theta R2. For the other guy, we'll have to do the same thing. So on the other way around, we have that M. So we're going to first need to get we need to get this HL, and we're going to just do it here, HL, just like we did HR. It's going to be the square root of, we have M squared plus they share the same plus D over 2. That's going to need to be a value that's going to be cached. Minus 2 M D over 2. Oh, wait. I can't do it like this. We need, oh yeah, so we're going to need to have M1 or MR, I should have said, theta ML, theta MR, and we have theta ML is going to be, what do we say? So just 180 minus theta MR. And now we can use theta ML here. Okay, so we have the H. I'm just doing it. Probably be coding this in something like this. So we have that HL, and now we need to. So we have this distance, and now we need to find these bad boys. So we do here. The first one is going to be this guy. So theta HL1. I need to redo that on paper. Theta HL2. HL1 will be inverse cosine of everything except for, everything except for HR. So D over 2 squared plus HL. So we're going to need to cache some values that, yeah, good thing I'm doing that. Yes. Okay, and then we have theta HL2 is going to be the inverse cosine of same thing as here. So it's going to be arm1L squared plus HL squared minus arm2L squared. And then we finally have, in this case, the angle for the this servo is actually going to be, so theta servo left is going to be just theta HL1 plus theta HL2, and so basically with this, if the input is just an XY vector whose origin is the middle of the center line between the two servos, the mirror line between the two servos, then that point can be reached by moving the two servos these two angles. Well, one thing to think about is also the swipes are not going to be um, very linear. They're not going to be very linear. From what I've observed, if you were to give it a start point and an end point, you would think that the servos would move the plotting point in a straight line, but in fact, I don't know what causes a little bit of an arc. Uh, uh, yeah, there would be an arc since these joints are just passive. They're what I could do is interpolate. So if I were, yeah, once, if the Arduino can do all the calculations, yes, because there's going to be a point where I have my thumb on the joystick and I'm moving top left, and then all of a sudden I want to move all the way across to bottom right. Now, what Unity so starting to the top left, Unity would send negative x, and y would send, let's say, negative 1, 1. And that's not even that's not a unit vector, but let's just pretend that's. Then from there, moving all the way back down. Question is, do I send this vector? Do I send this vector? Yeah, everything is going to be based from the center, so I'm stupid. I'm going to be sending, the vector that I'm sending is always going to be centered in the center of the joystick. Yeah, so, and it will be calculating accordingly, because if the servo arms, let's say, are up here like that, and then I send 1, negative 1, the point is going to be calculated from that center, from our center point down this way, and it's going to need, and then those angles are going to come up, and yeah, it's going to like and whatever it takes to reach that point. It's going to give me this angle and that angle. That's great. Yeah, never mind. That should work. That should work. What time is it? It's 4 o'clock. I have to pick up the kids, and so let me take a picture of this. Before I accidentally erase some of it, because then I just want to go directly to implementation. Okay. That should be the inverse kinematic. Well, only one thing we can do now is test it out. Let's see. So I can do it. The other computer has Visual Micro already set up. Let me think about how to do this. Do I just do this? Oh, it'd be nice to have both the code side and the video, because we're gonna look it up. An Arduino moving around, this thing. Well, let's show it off as it is right now. So let's use yeah, I wish the camera was over yonder. Okay, what? Oh shoot. God damn it. And let's oh yeah, and since I have visor, let me fetch visor. Let me see. Let's do try. But I have to reposition. Okay. Hmm. Oh shit. Of course. Oh god. I need a screwdriver. Already. I know how this feels already. As you start working on stuff, you start noticing that not everything is ready, and preparing the environment before doing any sort of work is super important. Like using tools for like ad hoc and placing where they need to be back and get more of a mess. And it becomes counterproductive very quickly. This needs to go. It's just hard to hook it here. God damn it. There we go. In your hole. Terrible lighting. And I did not expect to do any tinkering like this at this stage. Okay. What's going on? Is it this crane? Hold on. You know what? I did not test it with this phone. I tested it with this phone. So let's replicate the same test environment. Okay, visor. Connect, go. Installing visor APK? What? Okay, let's see. With this here phone, it was working yesterday. Go here, and we're going to do this. We're going to just say try. That's not cool. Oh, it's supposed to be grounded. Why is it not? It's too much pressure? Not enough pressure? What's going on? Yeah, it's that contact that needs to be. Okay. You know what? I'm gonna have to just use A hacked pen. This is not working like it was yesterday. What happened? Yeah, these used to just give me contact right away. What's going on? Oh. Let's make it even tighter. See what happens now, bitches. So here, there should be plenty. Too much? What we're gonna do? Just expose all of this directly inside this little Really? Is it just my screen that sucks? It is. Yeah. So, hold on, because this screen is a little bit cracked, if not a lot cracked. And it's gonna have to be 3D printed as well. It was fun in games and all, but oh, yeah, I'm gonna use some sort of plastic ball bearings for smooth transitions. Ah. Yeah. When it works really well. It's just the consistency. Ah. Yeah, that tip needs to be a little bit better. The sensor needs to be wide. Let's see it now. Oh, I need a break. From what I've seen, but in any case, from what I've seen, this seems to work at the best. It's a mess, but let's see if let's see if we can just hack something real quick. This doesn't work. How about this? And double-sided tape or anything. Any tape right now, I don't care. There we go. Just anything like this, I just want to see. That's not good. That's not a good sign. I thought this was going to work, no problem. It's these stupid heads. Oh, yo. Uh-oh. That's a problem. It looks like even just plugging in this cable ruins the whole. Oh yeah, yeah. That's not good. That is not good. That is not good at all. Oh yeah, that kills the fucking grounding. Damn it. Because this, just like that, it works. It works super fine. Look, even with a long wire. Yep, it works perfectly like this. But the minute I plug in this is plugged in, we're not responding the same way. Oh yeah. Yeah, it keeps on going back. Stuck. Yeah. Oh boy, what can I do? Shoot. I did not expect that. Let's try a different device. Oh, it's messed up. That is messed up. I did not see that one coming. As soon as I plug it in, and the whole voltage check is thrown off balance. Let's see with this. Oh. Well, if I have to make it use my own phone, then whatever. It looks like it's working fine here. Oh yeah, much better. Thank the goddamn Lord. Ugh. As soon as I do this. Yeah. Jeez. I don't know what the problem was, if it's the screen, the connectivity, the conductivity, the fact that this one is a Motorola Power, like specifically big battery, so maybe better insulation or something. I don't know. That, because now if we do this, well, let's get the that. This. Where's the other bar? Where do you go? Where'd it go? There it is. Yeah, well, not the sharpest tool in the shed. Oh yeah. So responsive. So responsive. Edit controls. Place it right there. Make it small. There. Let's do our fire. Fuck it, do it live. What happened? Oh, so it cannot be. Add a what program? Why is this constantly registering? That's what we'll need. Yeah, you know what? This solution is really good for solenoids. Yeah. If I had a solenoid there, normally the contact is perfect, but I can just lift the arm up to get recentered. Yeah, because there's the issue of I need to lift off to stop the contact, like a real thumbs. Okay, so, okay, it works, and it works with the video display. Jeez, I was freaking out there. What the heck? Why is the other ones now? What happened to you guys? This phone is worked perfectly yesterday. Yes, it's working fine here, right? But as soon as I plug it in, Yeah. See, it's doing the same BS. And by BS, I don't mean Brawlstars. Yeah. Okay, well. Okay, this definitely needs to be 3D printed. And definitely needs to be using solenoids. All right.